Okay, hello everyone. Today we will learn properties of point estimation, part 5. So far we learned how to find sufficient statistic, and also we proved that a function of sufficient statistic can become an MVU. However, we didn't discuss how we can find a function that give us MVUE. So in this section 9.6 and following section 9.7, we will cover how we can find estimators. So section 9.6 is method of moment, and section 9.7 is methods of maximum likelihood, and we will learn how to find estimators. Okay, let's move on to the method of moment. The method of moment is a simple procedure for finding an estimator for one or more population parameters. And the way is let us first define the moment. The case moment can be defined like this. The expected value of y to the case. Let us define this as case moment, and we can say the case sample moment. We can calculate the sample moment from the samples. From given samples, we can calculate the case sample moment, and the method of moment is that choosing an estimate those values of the parameters that are solutions of the equations of this for k equals 1, 2, and t, where t is the number of parameter to be estimated. So if you have 3 parameters, then you can have moment of m1 dash, which is e to the y, and you also calculate m2 dash is e to the y square, and m for 3 dash, which is e to the y third, and uh, and this is a function of parameters. If you have 3 parameters, this could be function of parameters, and you can estimate these using sample moment, case sample moment, mk dash, mk m1 dash, m2 dash, and m3 dash, and you have 3 equations and also 3 parameters, so you can calculate estimators for 3 parameters. So this is how you can use the method of moment to find estimators for some parameters. Let's move on to example 9.11. A random sample of n observations y1 to yn is selected from a population in which yi for I equals 1 to n possesses a uniform probability density function over the interval from 0 to zeta, where zeta is unknown. Use the method of moment to estimate the parameter zeta. So the density function for y is uniform from 0 to zeta. So it is 1 over zeta from y equals y from 0 to zeta and 0 otherwise. And to calculate, to use the method of moment, firstly mu1 dash is expected value of y for the uniform distribution. This is zeta over 2. And what is m1 dash? This is sample mean, which is sum of I equals to 1 to n yi divided by n. And so we set these as this is this, and then it gives zeta over 2 equals sum of yi over n. And so if we solve it for zeta, then zeta equals 2 times y bar. Okay, so this is 2 times y bar. So this is our solution, and this is our estimate for theta using method of moment. Let's move on to example 9.12. Show that the estimator theta hat is 2y bar derived in example 9.11 is a consistent estimator for theta. And to remind, the consistency is to proving this thing, and we were going to use theorem 9.1, which is an unbiased estimator theta and hat for theta is consistent estimator of theta if the variance of theta hat n goes to 0. So firstly, we need to prove that our estimator 2y bar is unbiased estimator. So to prove that our theta hat is an unbiased estimator, take expectation of this thing. This is 2 times expected value of y bar, which is since expected value of y is theta over 2 and variance of y is theta square over 12. And from here, you can derive that this is theta. And what's next? And for variance of 2y bar, this is 4 times n over 12 times theta square over 12, and so this is theta square over 3n. And as we can see that this one goes to 0 as n goes to infinity. As n goes large, this one converges to 0. So using theorem 9.1, we can prove that our theta hat 2y bar is consistent estimator, is a consistent estimator. Okay. Let's move on to example 9.13. A random sample of n observations, y1 to yn, is selected from a population where yi possesses a gamma probability density function with parameter alpha and beta. And for the density function of gamma, you can check section 4.6 for the gamma probability density function. And find method of moment estimators for the unknown parameter alpha and beta, and by checking the gamma distribution, you will know that expected value of y is alpha beta and variance of y is alpha beta square. And so you can use the method of moment estimator. Firstly, EY is alpha beta, and this is y bar. And what about expected value of y square? And this is actually variance of y plus EY square, And so this is alpha beta square plus alpha square beta square. And this is sum of yi square over n. Okay, and let's try to solve these for alpha and beta. So we have two equations. This is the first one, and this is the second one. Okay, and let's solve it for alpha and beta. So here beta equals y bar over alpha. So let's put it here. Alpha y bar square plus alpha square y bar square equals sum of yi square over n, and here alpha cancelled, and so um, this is y bar square 1 over alpha plus 1, or maybe let's put it this way. So from here, y bar square over alpha is sum of yi square over n minus y bar square, and alpha goes this side, and y bar square over sum of yi square over n minus y bar square. Okay, so this is our alpha hat. And what about beta? We can put our alpha here, this side, or let's alpha equals y bar over beta. Put this here, then we can find y bar beta plus y bar square equals sum of yi square over n, and so minus y bar square, let's move y bar this side, and over y bar. Okay, so our beta hat is sum of yi square over n minus y bar square over y bar. Okay, so so this is our beta hat, and this is our alpha hat. Okay, they are method of moment estimator for parameter alpha and beta. Okay. Okay, let's try one more exercise problem, which is 9.78. Let y1 to yn denote independent and identically distributed random variables from a power family distribution with parameter alpha and zeta equals 3. Then, as in exercise 9.43, if alpha is greater than 0, the density function is like this, and show that expected value of y1 is this, and derive the method of moment estimator for alpha. Okay, so the first problem is to find expected value of yi, and to do that, this is integration from 0 to 3 y times alpha y alpha minus 1 over 3 alpha dy, and this is y to the alpha, and so and 3 to alpha over alpha are constants, and alpha plus 1, y to the alpha plus 1, and from 0 to 3. Okay, and this is if okay, 3 alpha 3 to the alpha plus 1, and alpha plus 1. Okay, so this one is 3 alpha plus 1. Okay, so this is same as this one, and so we showed that the expected value of y1 is this thing, and to use the method of moment estimator, this is mu1 hat, and we will put it this is y bar, and so 3 alpha equals y bar alpha plus 1. This is y bar alpha plus y bar 3 alpha, and minus y bar equals y bar minus 3 alpha. So alpha is y bar minus 3 minus y bar. Okay, so our method of moment estimate would be this thing. Okay. Homework for chapter 9.6 are these. Let's move on to the section 9.7, which is the method of maximum likelihood. An idea behind this method is we want our estimator to maximize the likelihood given the dataset. And what this means, and to understand it easily, I will give you a simple example. Suppose there are 3 balls of red and blue in the box. So we have box and we have 3 balls of red or blue. We don't know this ball is red or blue, and we randomly draw 2 red balls. We randomly drawn 2 red balls, and given the situation that we drawn 2 red balls, how many red balls do we have in the box? So the parameter is the number of red balls. So in this case, we want to estimate the number of red balls. The number of red balls, it is hyperparameter. This is the parameter we want to estimate, and actually, from the dataset, the situation is one of these two. So for the first situation, we can have 2 red balls, and also we can have 3 red balls. What is more likely? What situation is more likely? So we from the data we choose 2 red balls, and what would be the situation? And we can calculate the likelihood, how likely we can find 2 red balls from this situation, or how likely we can sample 2 red balls in this situation. So the probability is that in this situation we are choosing 2 balls from 3 balls, and we in this situation we are choosing from 2 red balls we choose 2, from 1 blue ball we choose 0. So this is the probability for this situation. And what about probability in this situation? We are choosing 3 to 2, and also we are choosing among 3 red balls we choose 2 balls, and among 0 blue balls we choose 0. And this probability is 1, and this probability is 1 over 3. And so which is more likelihood? So this situation is more likely. So we can take our estimator for number of red balls is 3. So this is the idea behind method of maximum likelihood. So in the method of maximum likelihood, suppose that the likelihood function depends on k parameters, theta 1 to theta k. Choose as estimate those value of the parameter that maximize the likelihood. So this is the likelihood given the data. So here is data y1 to yn are data sets that are given, and the likelihood is the probability, the how probable the situation is. The likelihood function, it measures how likely the data is, and what we want to do is that we want to maximize this likelihood with respect to the parameter theta 1 to theta k. That's how maximum likelihood works. Okay, let's learn this method by examples. Okay, let's move on to example 9.14. A binomial experiment consisting of n trials resulted in observations of y1 to yn, where yi equals 1 if the ith trial was a success and yi equals 0 otherwise. Find the MLE, maximum likelihood estimator, of P, the probability of a success. From this problem, what would be the likelihood? The likelihood of data y1 to yn of P can be defined. So the likelihood of the data is the probability of the given situation, given data, and so this is the product of each probability mass functions. So product of I equals 1 to n, the probability mass function is p to yi times 1 minus p to 1 minus yi, and so this becomes p to sum of yi 1 minus p n minus sum of yi. Okay, and from here, if we are maximizing, we want to find the value that maximizes this function, and actually it is same as calculating the value. So if there's a continuous function, so ln maximizing this maximizing finding value that maximize this function is actually equal to finding value that maximize ln l y1 to let's say this lp lnp. Okay, so the ln of lp, likelihood of p, is sum of yi times ln p plus n minus sum of yi 1 minus p, and yeah, ln 1 minus p, 1 minus p. Okay, and to find the value that maximize this, so the function, the shape of the function may be something like this. This is the shape of LP and ln LP, and to calculate, to find the maximum value, the user trick is that get the derivative with respect to p. So dp equals 0, then we can calculate, if we set it 0 and then solve it for p, then we can calculate this p hat. And also, if we want to make sure that the shape is this thing, then we need to calculate one more derivative. The second derivative of lp is less than 0, d square p. So we can, if we check these two conditions, then actually this second derivative at p equals p hat. Okay, if we find this condition, then the p, the likelihood is maximized at p hat. Okay, so from here we differentiate with respect to p, d ln l p dp, and this is sum of yi over p plus n minus sum of yi 1 minus p, and the derivation of 1 minus p is minus 1. Okay, and let's set this 0 and solve it for p. Then we will get 1 minus p times sum of yi equals p times n minus sum of yi, and this is sum of yi equals np. The p times sum of yi part cancelled, and so our p hat is sum of yi over n, which is y bar. So this is our MLE, and actually to make sure the LP is maximized at this position, actually we need to calculate one more thing. The second derivative of this thing is minus p square sum of yi, and from here minus 1 minus p square minus 2 minus and minus comes again, so this is minus, and so this is n minus sum of yi, and actually this one is positive, this one is also positive, so negative of those positive is negative, so this is negative. So we can check that these two conditions and confirm that p hat equals y bar is our MLE. Let's move on to example 9.15. Let y1 to yn be a random sample from a normal distribution with mean mu and variance sigma square. Find the MLE of mu and sigma square. And for normal density, f of y is 1 over square root of 2 pi sigma square e to the minus y minus mu square over sigma square. Okay, so what's the likelihood? What's the likelihood of data y1 to yn, mu and sigma square? And the likelihood of the data, since y1 to yn are independent, this is integrating, multiplying all these densities. So it is 2 pi minus 1 over 2 sigma square minus 1 over 2 expected e to the minus yi minus mu squared over sigma square. And let's take ln to this L, mu and sigma square, and this is minus n over 2 ln 2 pi here minus n over 2 ln sigma square, and minus sum of yi minus mu squared over sigma squared. Okay, yeah, so from here the way we can find the MLE is we want to we can get the derivative with respect to mu. And so the with user trick, what we can do is get the derivative of with respect to mu that is equal to 0, and also we get the second derivative of this thing, and this is less than 0 at mu equals mu hat, then we can say that the likelihood is maximized at this mu hat position. We solve from here, we solve mu hat, and so to do that we get the differentiate on this thing. So Ln L mu sigma square d mu, and this is actually these do not depend on mu, and this one only depend on mu, and this one is sum of yi squared minus 2 mu yi 2 mu yi plus mu squared. And so this part is so if you differentiate with respect to mu, then it is actually here we have minus, so plus 2 sum of yi minus 2 n mu. So, and this part is 0, and if you solve it for mu, then mu hat is sum of yi divided by n, so this is y bar. So this is our estimate for mu, and if you get the second derivative, then this is minus 2n, which is less than 0, and so our mu hat is MLE. The likelihood is maximized at mu hat is y bar. Okay, and then let's move on to sigma square part. Okay, let's move on to example 9.15. Let y1 to yn be a random sample from a normal distribution with mean mu and variance sigma square. Find the MLE, maximum likelihood estimator, of mu and sigma square. And the density function for normal is fy is 1 over square root of 2 pi sigma square, and e to the minus y minus mu square 2 sigma square. Okay, and so the likelihood of data y1 to yn mu comma sigma square is the product of each density functions. Since y1 to yn are independent, the likelihood of the data, the probability, how probable is the data is, that's the product of density functions. And so this is 2 pi minus 1 over 2 sigma square minus 1 over 2 and e to the minus y minus mu square over 2 sigma square. And this is actually 2 pi minus 2 to n over 2, and this is sigma square minus n over 2, and this is e to the minus sum of I equals 1 to n yi minus mu squared over 2 sigma square. Okay, and let's take a trick to get the we want to find the value that minimize this likelihood, and actually the notation is something like this, and it's harder to get the derivative and find the minimum. So the user trick is taking a log, take log of L mu and sigma square, and this one we can easily get the derivative and find the value that that maximize this likelihood function. So we take log, and then we can get minus n over 2 ln 2 pi minus n over 2 ln sigma square and minus 1 over 2 sigma square sum of I equals 1 to n yi minus mu squared. Okay, so this is our log of likelihood function, and we want to find the estimators that maximize this likelihood function. We want to find the value mu and sigma square that maximize this value, and to get that values, what the usual trick is get the derivative and that equals to 0. And so the user trick is differentiate with respect to mu and set it to 0 and solve it for mu to find mu hat equals something, and also check for mu second derivative to at mu equals mu hat. So this condition implies that so this is our function, and at mu is mu hat, the second derivative is less than 0, implies that this is the maximum position of this function. So we want to check this too, and so let's get the derivative of this function. So derivative of mu sigma square is and these two parts are not dependent on mu. Only this part is dependent on mu. So this one is actually this part is sum of yi square minus 2 sum of yi mu plus n mu square. So this part can be written as this, and also since we have minus 1 over 2 sigma square, so 1 minus 1 over 2 sigma square, and we get the derivative with respect to mu. This is minus 2 sum of yi and plus 2n, and we set this 0 and we solve it for mu. Where is mu? 2n mu. Here, sorry. And then if we solve it for mu, then we can find that mu hat is sum of yi over n, which is y bar. And also, what would be the double derivative, second derivative with of this thing, and it is 1 over 2 sigma square, and here this part is 2n, and this is less than 0. So so we can confirm that mu hat at mu hat equals y bar, the likelihood function is maximized. So this is our MLE for mu, and let's move on to find the MLE for sigma square. Previously, we calculated the log of likelihood this way, and let's try to find the MLE for sigma square this time. So we get the derivative with sigma square, mu sigma square, and this is 1 over n over 2, 1 over sigma square, and let's see, plus 1 over 2 sigma square squared, and sum of yi minus mu squared. And let's set this 0 and solve it for sigma square. And we can cancel one of these, and we can cancel 2, and then we can find that sigma square hat is sum of yi minus mu squared divided by n. And so let's put mu hat here. Then our sigma square hat MLE estimate, it becomes sum of yi minus y bar square over n. Okay, and actually we need to check one more thing, which is second derivative ln L mu sigma square, and this is plus n over sigma square squared, and this is minus sigma squared third, and we have let's see, minus e. Actually, we have 2 here, 2 here, and 2 sum of yi minus mu squared. And actually, this time it is harder to check whether this is less than 0, but we should put our from this formula we should put sigma sigma square hat here and mu hat here, and actually if you put these things here, and then you can find that this one is less than 0, and so this condition also holds, and you can make sure this is our MLE as well. So what we conclude is that, and actually let's just finish it. So this is n over 2 times n over sum of yi minus y bar squared, and minus 2 times n over sum of yi minus y bar squared third, and here 2 times sum of yi minus y bar squared, and we can put n here, and cancel one of these, and let's see, 2n. Okay, then this one becomes since these are same, this is minus n over 2 sigma square hat squared, and which is less than 0. So we also checked that the second derivative is less than 0 at our MLE position, and so we can conclude that the mu hat is y bar, and sigma square hat is this thing, and as we can see, the y bar, this is our unbiased estimate, and the sigma square hat, this is biased estimate, but biased estimator, but we can modify it a little bit to make it unbiased estimator. Okay. Let's move on to example 9.16. Let y1, y2, yn be a random sample of observations from a uniform distribution with probability density function of this thing. And for yi is from 0 to theta, and I equals 1 to n, find the MLE of theta. Okay, so this is uniform distribution. Okay, so let's define our likelihood function. Likelihood function from y1 to yn given theta is actually 1 over theta times 1 over theta times dot 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 1 over theta. There are n number of density functions, and also we have 0 and y1 to yn, and actually let's use order statistic. So y1, this is the smallest, y2 is the second smallest, and yn is maximum of yi's, and this is less than theta. Okay, so this is the function. So y1 to yn are given, and so this L theta is 1 over theta nth, and we know that yn is less than theta, and from here actually we can draw this graph, and this is if theta is yeah, the graph should be look like this. And also the restriction is that here is our yn, the maximum of yi, and actually theta is greater than yn, so theta is greater than yn, and our L theta is defined on here. And what we can check is that this function L theta, this is our function L theta, and this L theta function is maximized at this position. At this position, this function is maximized. So our theta hat estimate is the maximum of that yn, which is maximum of y1 to yn. So this is our maximum likelihood estimator for this uniform distribution case. Okay. Let's try to solve exercise question 9.94. Suppose that theta hat is the MLE for parameter theta. Let t theta be a function of theta that possesses a unique inverse. That is, if beta is t theta, then theta equals t inverse beta. Show that t theta hat is the MLE of t theta. It is very useful technique. So if we solve this exercise, then to find the MLE of t theta, we can just find the MLE for theta and put t theta hat to find the MLE for t theta. So what this means is that if you know that theta hat is MLE for theta, then MLE for t theta is just t theta hat. for the function in here, the t is one-to-one function. So with this restriction, you can easily find the MLE of t theta. Okay, and let's prove this exercise question. So since theta hat is MLE, the likelihood of theta hat is always greater than or equal to L theta. Because theta hat is the maximum maximize the likelihood function, so L theta hat is always greater than equal to L theta. And also here's the trick. Actually the maximizing L theta is actually same as maximizing LT theta. Oh, no. Let's think about different way. So we want to solve L beta. We want to find the beta hat that maximize L beta, and actually finding beta hat that maximize L beta is same as finding beta hat that maximize L T inverse beta. So any beta hat that maximize L beta would maximize L T inverse beta. So we want to find the beta hat that maximize this one, and this one is actually L theta. And actually L theta can be maximized as theta hat. So L theta hat at L theta hat, this function is maximized, and actually this one is L T inverse beta hat. And so and so um, so and so this one so actually this function is maximized at beta hat, so this L beta is maximized at L beta hat. So it's maximized at L beta hat. So actually this is the proof. The beta hat is MLE for beta. Beta hat is MLE. Actually, this is T theta hat. T theta hat is beta hat. Okay. Let's move on to example 9.17. In example 9.14, we found that the MLE of the binomial proportion P is given by this thing, which is here y is actually sum of yi's, so P hat is actually y bar. What is MLE for the variance of y? Variance of y. If y follows binomial and p, then variance would be npq and p1 minus p. And let's define the function tp as np1 minus p. Then the MLE estimate is just putting p hat here. So MLE for TP is TP hat from the previous exercise problem. So the MLE is N y bar 1 minus y bar. So this is our MLE. Yeah, okay. Homework for section 9.7 are these. Okay, so far we learned the properties of point estimators, and we also learned the methods of estimation, and uh, and let's move on to chapter 10, which is hypothesis testing.